This is the last video on this handout. One more thing about delta prime and how it relates to this differential equation we've been studying for the whole time, really. We're going to put the damping term in for, we've done that just a little bit. I'm going to put it back in, and we'll see it gives us a slightly more interesting answer, more complicated answer from the point of view of distributions. Mainly, this is going to be a nice excuse to think about a useful little lemma about how to work with distributions and derivatives that is in the solutions. It's presented as part of the alternate solution to this. So we've got our standard differential equation. We're back to zero forcing, at least the usual kind of forcing. And the usual perspective is we start out with y of 0 equals y naught, zero velocity, just to be simple. And so suppose y of t is the usual solution, which is like an exponentially damped cosine, etc., etc., etc. Not particularly crucial to us. I don't want to imply it's wrong, but we're not actually going to need the explicit formula. And then we're going to take y of t times h of t to expand this perspective of it's always been there, and then it's suddenly had this jump, and then started oscillating freely. And we want to know in this situation, what is the appropriate forcing that does that jump? It's not going to be exactly just a delta prime, because this is going to give us a slightly different term. Okay, so the question is, if you take this as your function and you plug it into the left-hand side here, and you differentiate it as a distribution, what do you get over here? Okay, so the idea is, I've said this before kind of vaguely. Oh yeah, so I'm going to skip the first solution in the solutions PDF, which just cranks it out with test functions, and I want to start to get away from that. Okay, so the idea is, we know this is boring, and this is just taken care of by whatever function is appropriate here. It's just the jump that really should be at issue. That's the only thing that should require something to happen here. In other words, we should get some sort of distribution that's supported exactly at the origin. Something involving deltas and delta primes, most likely. Okay, so here's what we'll do. Okay, we'll separate this out into a jump and a continuous function. So let's let f of t be y of t minus y naught h of t. Okay, what's the graph of that going to look like? It's going to go along, and then this is going to slide down, and so it's going to be continuous and actually differentiable. But then it's going to start wiggling down here at a minus y naught level. Okay, and that is a nice continuous differentiable function, and so hopefully that's not going to create any deltas when we put f into here. And then the deltas are just going to come out of what happens to the h of t. Okay, so we need a little bit of a lemma. I guess I call it a claim in the PDF, the solutions PDF. Oop, I shouldn't have erased that. That's okay. Well, I'll bring it back. I want the picture though. Okay, so the claim, let's just bring in some anonymous function g. So if g is continuous, so no jumps, and let's say it's piecewise differentiable, so it could have some sharp corners, okay, and when you take g prime of x, you get some function h of x in the usual way, but just everywhere where that's meaningful, everywhere, and let's just have a name for where it's going to go wrong, x everywhere but on a finite set S. And it doesn't really just have to be finite, and later on we'll get much more interesting about where this could fail to be differentiable and still have this kind of result. Okay, a finite set S. Okay, so actually, you know what? That's too special a picture right now. So here's G. It's la 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 sharp corner, la 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 sharp corner, la 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 sharp corner. Okay, and here's S. Like x1, x2, and x3 is going to be S. Okay, except on a finite set S. Okay, then G prime is going to be just H as distributions. We know that if you have a function H, you can turn it, as long as it's integrable, let's say, then you can turn it into a distribution. And even if I don't know the values on a finite set S, who cares? That's not useful. That's not necessary to know. We can redefine it as at will. Okay, so just define it whatever as at those points if you want to, and then G prime as a distribution is going to be H. The main thing is that it's just a function. and there's no deltas. Okay, that's quite a contrast from, say, the derivative of the unit step function, which is piecewise differentiable, but not continuous. It has a jump. Its derivative is not a function. It has deltas. Okay, so the punchline of this is the derivative of a continuous function, because it has no jumps, should have no deltas. It should just be the kind of distribution that comes from a function. Okay, so if you want to see the careful proof of that written out with test functions and integrals and everything, go ahead and look at the PDF. Hopefully it's fairly intuitive that if there's no jumps, then when you take the derivative, you're not going to yet introduce deltas into the mix. Okay, so now let's assume that, and then it's going to be easy. Okay, so remember f of t was y of t, h of t. Well, I don't know if I said that right. Yeah, y of t, h of t minus y naught h of t. So that's the function extended to be the jumpy guy, but its values has values for all r, and then slide the right half down to be so the thing is continuous and differentiable. So now our claim that applies to f and to f prime. So it is important that not only there's no sharp corner here. Now there's a sharp corner in f prime, but no jump in f prime. Okay. Okay, and so that means that we can apply, when we look at this combination, here, of course it's a function. There's no deltas in it to start with. Here we've taken one derivative, no deltas. Here we're taking two derivatives, but because at the first derivative level it had no jumps, this has no deltas. Okay, so this is going to be, we can take its derivative in the ordinary way, and if there's some finite number of points where it doesn't seem to make sense, just ignore them. Okay, what's going on here? Well, it's certainly 0 here. Now here, it doesn't solve the homogeneous equation anymore. It's going to solve the equation where this has been turned on. The minus y naught has been turned on. Well, that's a constant, so it dies here, and so we just get a minus k y naught. But that only happened after the shift turned on, and so it's minus k y naught h of t. Okay, so that is something, and I'll just put h because it's really as distributions. Okay, so again, what we did was we did a calculation that works almost everywhere but at the origin as ordinary functions, and because we know this hasn't yet done enough weirdness to create deltas, it's actually true as distributions on all of R. We're not sort of secretly, by ignoring the origin, x equals t equals 0, we're not suddenly ignoring some important delta thing. And that's because we've engineered f to be once differentiable everywhere, and so it can't create deltas even when you get to the second derivative. Okay, now it's a simple calculation. What was y? The thing we actually want is this with the jump back put back in as a distribution here, okay? And then we just plug everything in. Okay, so my double prime plus cy prime plus ky. Okay, that's going to be that stuff applied to f, which we now know what happens as a distribution. That's going to be easy, okay? Plus y naught times the same operations. Oop, there's an m, yeah. mh double prime plus ch prime plus kh. Okay. So this all gives me a minus k naught h, and surprise, surprise, that cancels the y naught kh here, okay? And then plus, and here's the punchline, we get an my naught delta prime, which is what we got before. Ooh, that's not showing up very well, is it? Okay. Plus, and this is the new thing that comes from the damping term, a cy naught delta. Okay. So that's gonna, so it's just gonna die. Okay. Because these guys cancel. So this is the punchline where if you want to just do a jump up when you have second derivatives and first derivatives, it is a little tricky. It is a little complicated. You have to hit it with the double hammer, but then you also have to hit it with the single hammer as well, the delta, in the right portion. So again, for me, I think the interesting thing is this idea that if you've got a function that it seems that its derivative has no jumps, it really is true. The derivative has no deltas because the function itself has no jumps. Okay, that is it for that handout.